everyone. Today I'll be talking about a memory-based runtime-reconfigurable mixed-radix hardware Fft generator in Chisel. So first, FFTs are everywhere. Hardware FFTs have been re-implemented countless times, and their core DSP in everything from radio astronomy, audio signal processing, MRI, and software-defined radio. So if we just look at wireless communication, we think, okay, all the different standards that are involved, everything from Internet of Things, which requires, doesn't really have a significant has an extremely significant power constraint, but doesn't have as stringent of a throughput requirement, all the way to digital TV, which requires high data throughput, but doesn't have as much of a limitation on power. All of these different different standards require different FFT or other DSP block configurations. So this implies that one-off designs, whether they're runtime reconfigurable or otherwise, aren't resource and time efficient from a designer perspective. Also, in the case of LTE and Wi-Fi, you actually need to support runtime reconfigurability. So how do we approach hardware DSP design? Well, we don't really want to reinvent the wheel. We want to leverage our understanding of algorithms and architecture regularity, and instead of building instances, build generators. So generators support a wide range of applications. This enables you to do fast systems prototyping and design space exploration. They allow you to, if you design a generator well, give you state-of-the-art performance. And unlike commercial runtime reconfigurable IP cores, which target specific applications like LTE, for example, you're able to get an extensive and also an extendable feature set with the help of the open source community. So how do we approach this? Well, it's actually the same general approach as one-off instance design, but we just need to change our mindset slightly. So if you look at prior art for memory-based FFT instances specifically, you'll see that a lot of the papers focus on one aspect of the FFT design. For example, how do you come up with conflict-free calculation schedules using multiple butterflies, but they don't consider the implications of this enhancement, so to speak, on the overall system complexity. And in the case of conflict-free calculation schedules, how does it affect, for example, input-output addressing or even like twiddle memory usage? So moving on from FFT instances, if you were to look at FFT generators, you'll see none of the current ones that exist in that are available for users support runtime reconfigurability. Spiral from CMU requires foreign memory, and their algorithms are limited to fixed 2 to the n FFTs. Stanford's Genesis 2, for example, also doesn't support I/O unscrambling. So how do we develop FFT hardware generators with an FFT as an example? So smart design choices benefit both instances and generators. So if you look at the standard Radix 2 Cooley-Tukey FFT signal flow graph, you'll see that there are sort of rules that govern how twiddles are computed, how inputs and outputs are connected, and general interconnect patterns. And these rules can be applied for whatever Radix 2 FFT size you care about. For example, if you look at the twiddle factors of subsequent stages are always a subset of the previous stage's twiddle factors. And also, for Radix 2 FFTs in particular, if you look at a decimation and frequency signal flow graph, the inputs are indexed in order, the outputs are indexed in bit reversed order, and for decimation in time FFT, you actually get the reverse of that. So this is actually kind of problematic if you just naively think about an FFT design, because you have this bit reversed unscrambling step that needs to occur. You assume that I/O cannot be performed in place. And this will limit you in saying that, okay, maybe you need a 3N memory design if you wanted to support memory-based FFTs. So your first symbol goes in memory A, it's then calculated on, and then the output gets output, and it requires 3 memories to keep the pipeline going. However, leveraging the fact that decimation in frequency and decimation in time signal flow graphs are actually mirrored images of each other, you can basically allow you to switch between decimation in time and decimation in frequency every 2/8 symbol, allowing you to do in-place computation with only 2N memory. So for example, symbol 0 is input in decimation and frequency, like indexing. It's calculated using the standard decimation and frequency signal flow graph, and the output is actually using the decimation and time index mapping, and then vice versa happens when you start feeding in symbol 2. So then you can perform in-place readout, basic in-place memory reads and writes, and then by allowing you to switch from 3N memory to 2N memory, you're able to save 33% reduction in memory, which is great for power and area. So if you wanted to generalize from standard radix 2 or power of 2 FFTs to 2 to the n, 3 to the m, 5 to the 7, 5 to the k, 7 to the l, etc., you could use the Cooley-Tukey algorithm, which is what you use, which was applied before. But with Cooley-Tukey, you actually have to compute additional twiddle factors. And if you leverage the fact that mixed-radix FFTs can be decomposed into coprime elements, you're able to use the prime factor algorithm followed by Cooley-Tukey recursively for scalability, and this minimizes the number of twiddle factors needed because the prime factor algorithm is actually a true bidirectional transform. So similarly, you can apply the decimation in frequency and decimation in time duality exploited with the 2 to the n FFT for the more general case, but you need to, so to speak, unlock dual index mappings, and this would allow you to achieve in-place I/O with 2N memory. Even more generally, you'll see that the same rules and optimizations that you apply for a 24-point FFT applies to a 60-point FFT or an 864-point FFT, and this leads to the conclusion that you can compile time and you can perform reconfigurability at compile time or at runtime via parameterized control logic. And this is actually really nice because it's extensible to using Chisel for generators. So briefly, Winograd's short Fourier transform algorithm allows you to reduce the number of hardware-intensive multiplies you need in favor of an increased number of adders, exploiting cyclic convolution. Specifically for the radix 2 case, just if you were to look at a radix 2 butterfly and a radix 3 butterfly, you'll see radix 2 butterfly requires 2 complex adders, radix 3 butterfly requires 6 adders and 2 multipliers, and obviously radix 3 requires more hardware resources than radix 2. So if you wanted to support a bunch of different wireless standards, for example, including Chinese digital television, which requires this nasty 3,780-point FFT in radix 7, you would get a butterfly that can look something like this. This has a bunch of additional registers and other logic inside that allows you to support runtime reconfigurability, and that means that I'm reusing radix 7 hardware for other radix modes. And all of the multiplication constants there are programmable. So at any given time, you're using up to 36 adders and 8 multipliers. For example, if you wanted to use this radix 7 butterfly for radix 3 at a particular computation step, only the elements in purple are active. So for the radix 3 case, you'd reduce it down to 6 adders and 2 multipliers that are active. So that was talking about runtime configuration. If you wanted to look at compile time configuration, this radix template, this butterfly template, supports custom stage pipelining and also tunable internal bit growth, so you can perform some design space exploration and optimize for this. Also, you achieve optimal stage bypassing with unused radices, and that means that I have this template that supports runtime reconfigurability from radix 2, 3, 4, 5, and 7, but for example, I only want to generate a 2 to the n FFT. So instead of basically this butterfly template just ends up reducing down to a radix 2 only output for hardware if you only need that case. So as you can see, unlike a standard IP core, which is only configurable at runtime, you're actually able to save area if you don't need it. So for Cooley-Tukey, as I mentioned earlier, for 2 to the n FFTs, it basically allows you to recursively and uniquely map an index, for example, n, to a vector. And these 2 index mappings give you this bit-reversed relationship between the input and the output. If you were to generalize that to mixed-radix FFTs, you might think, okay, instead of bit reversal, how about digit reversal, right? That makes sense. But one of the things with digit reversal is if you wanted to support prime factor algorithm in addition to Cooley-Tukey, and you wanted to be able to support in-place continuous I/O, Rather than using the more frequently quoted Chinese remainder theorem or good mapping, you actually want to use a more general 1D to 2D index mapping, and this can actually be simplified into Cooley-Tukey for specific cases. But then in the prime factor case, you have this particular mapping that allows you to reverse the decomposition order between, for example, decimation in frequency and decimation in time equivalent. That allows you to say that the K decimation in frequency output is the same index mapping as the N decimation in time mapping. And this allows you to use the same index counters for either forward or reverse decomposition and allows you to achieve in-place I/O with 2N memory. The downside for all of this is you have this nasty mod unit, which is not really hardware friendly. But if you design all of your logic and think of everything in terms of mixed-radix arithmetic, actually mod operations are free, because I'm just, instead of masking out bits, I'm masking out digits. And the unscrambling scheme, when I do prime factor followed by Cooley-Tukey decomposition, is actually not specific to FFT flavors, and you still apply the digit reversal at the end. So that was talking about the FFT I/O. If you now look at the FFT calculation step, right, the simplest case for a memory-based FFT is you have a single butterfly iterating down this signal flow graph. And if you do that for LT and Wi-Fi sizes, worst case, you require 2x the clock rate to compute the full FFT, for 2x calculation clock rate to compute the FFT. But even if you look at that, for 648 and 864 point FFTs, the compute doesn't finish in 2N. So this kind of makes you think, given a specific throughput constraint, what you really want to be able to do is use the optimal number of parallel butterflies so that you can achieve, for example, finish your computation in only n cycles. Unfortunately, this complicates conflict-free scheduling. So let's stare at the signal flow graph some more and take for now that banking relies on the mixed-radix representations of operand locations. A couple of observations you'll note is that radix 2's stage has the most butterflies, but they don't have any twiddle multiplications. So you can reorder the butterflies and parallelize them without incurring bank conflict. If you were to do that, this is actually what was taped out 2 years ago-ish now, 3 years ago. You'll see that I was able to reduce the number of compute cycles needed from something that was exceeding 2 in these two cases to below 2, and you can similarly reduce for some of the other FFTs. So how do you generalize this for mixed radix case? Well, if you look at an n equals 48 calculation schedule with one processing element, as each of the stages are iterated through, you're actually just counting the processing elements. The digits associated with a particular stage are zeroed. And this banking scheme allows you to guarantee that all the operands for a single processing element come from different banks. But for example, if now you wanted to do 2 processing elements in parallel, you'll see that the first and the second row have conflicting banks, and therefore you can't actually accomplish this. So now if you were to look and say, okay, the maximum radix that's needed for a 48-point FFT is 4, and for example, you wanted to be able to support 4 processing elements in parallel, then instead of using 4 memory banks, you actually want to have 16 memory banks accessed simultaneously. You can change the banking scheme to ensure that that's all possible. All the memory locations are processed, and you can achieve this basically by reordering when reordering the digits used to count the processing elements. And now you'll see that all 4 of these can be grouped in simultaneously with the rest, and none of these banks conflict. So all of these concepts were used to develop this FFT generator. The FFT generator is built in Chisel. It includes what I call hardware template, which just has lookup tables for reconfiguration and twiddle factors. They have controllable blocks, configurable blocks controlling data flow between the I/O, the SRAMs, and the processing element. And actually, as would be expected for a memory-based design, the design complexity is mostly in the control logic. This hardware template is populated after some processing work done by what I call Scala Firmware. This firmware takes in user inputs, for example, the desired FFT length, and calculates constants for lookup table generation and also hardware parameters. For example, the FFT length determines the number of banks, memory banks, how large these memory banks need to be, and the specific butterfly radices that must be supported. They also are used to basically calculate the size and also the contents of the twiddle lookup tables with the help of the Breeze Scala numerical processing library. So this is a more full-blown picture of what the firmware does, and essentially, after the user inputs, it turns on it for a little bit, outputs a hardware template, populates the hardware template in Chisel, and also populates a test vector generator that creates test vectors that can be usable all the way down to post, place, and route design for verification. So this is what I aimed to actually apply my FFT generator to originally. It supports Wi-Fi 802.11ac and LTE. Specifically, Wi-Fi and LTE, if you just don't ignore the stuff on the right, requires reconfigurability for power of 2 FFTs, with the exception of this 1536, which is 512 times 3. But if you wanted to support SCFDMA pre-coding for LTE, you actually need to support this wide assortment of 2N, 3M, 5K FFT sizes. And actually, once you figure that out, 7L comes for free, and you can extend on to other prime radices. So if you were to look at static versus runtime reconfigurable FFT areas, you'll see A, for memory-based FFT, chip area is dominated by SRAM, so if you're able to save 33%, that's great. And also, if you wanted to support all Wi-Fi and LTE sizes reconfigurably, compared to just a standard n equals 2048 point FFT, you only have a 24% area penalty. So this kind of touches upon some of the stuff that we were working on with Chisel DSP. You can integrate this FFT generator with more general DSP infrastructure that allows you to verify mathematical correctness and decouple algorithmic errors from degraded performance due to quantization noise by allowing you to plug in, for example, either fixed point types into the FFT or DSP reals, which are just essentially wrappers on system Verilog reals, and this allows you to study system sensitivity to block level performance. And one of the nice things is because we're designing in Chisel, we can verify block functionality in a system model that's constructed partially with synthesizable hardware and also with non-synthesizable Scala models. And the same infrastructure can be used, and although these interfaces don't necessarily need to be cycle accurate, they allow you to do fast systems exploration and prototyping. So this is the FFT accelerator that was taped out in Craft in 16 nanometer. Basically, it's attached to a Rocket RISC-V core and also has this hand laid out ring oscillator. This was in 16 nanometer. It was taped out within 1 month from when we got our first 16 nanometer FinFET PDK. And basically for control, the Rocket chip just sets up the FFT for a particular FFT that you want configured at runtime, and then feeds in the data, waits until it's output, and you can do all the testing in C. So the performance is comparable to state-of-the-art. This same FFT generator, now translated from Chisel 2 to Chisel 3, was used in a real-time 1.89 gigahertz bandwidth, 175 kilohertz resolution sparse spectral analysis RISC-V SoC, also in 16 nanometers. The ADCs were designed using the Berkeley analog generator. They were actually modeled first in Chisel because they were swapped with the real IP in Innovis. And thankfully, the modeling worked. It also included Mixed-Radix FFTs that came from this generator and a peeling reconstruction backend that was designed in Chisel. So in this case, the Chisel and the bag generators enabled the first automatically generated, fully integrated sparse spectral analysis SoC, and it was designed in 2 months. So the code for the tapeouts can be found here, and the work was sponsored by NSF, DARPA, BWRC, Aspire, and Adept. Thanks.
Angie, do you want to take questions? Yeah, so if anyone has any questions, they can come up to this mic in the middle. I can start with an easy one, maybe. If you have a bunch of different FFTs that you want, but you want them to be configuration, like non-runtime configurable, can you still share resources between them?
That's a good question. That's actually not supported, but But for example, if you wanted to compose your own FFTs with the, you want them to be different radixes. You can't share resources, but you could potentially reuse some of the blocks because I implemented it kind of in unit elements to implement like an alternative that would be able to do that.
I guess, do you see these techniques as being generalizable to other similar transforms, like wavelet, for example?
In the sense that you can like create, for example, DCT transforms using FFT hardware.
Just like Chisel code, generally, like do you see a way to use Chisel to make library of components that are extensible to other transforms?
I definitely think that's the case. You just have to basically zero in on components that you think are reusable amongst all the different algorithms and transforms that you care about. Don't create a big jumbled mess of like for one particular instance, but you have to systematically think, okay, I want to partition it some way because I think this block is more reusable.
So you have a very parameterized design here.
Yeah.
What was missing from Chisel in the beginning, and what was added in order to be able to do all the fancy stuff that you were doing?
Man, it's been a while now. So for me, like actually just not having any complex type support originally was a big pain. Having to do all the manual floating binary point conversions myself was one of the reasons that we decided we should come up with Chisel DSP and try to simplify the design process for DSP hardware engineers. There were some bugs in Chisel 2 that were like, man, I think this should be right, but it's not. And is it my fault or is it Chisel? I'm not really sure, but I think they've actually cleaned that up a lot. And now when you use it, it's just like the design productivity increase, I think, is pretty significant, especially if you want to design generators that are parameterized and even potentially runtime reconfigurable. So.
All right, let's thanks Angie again. And our next speaker